Thank you, Lisa, for the kind introduction. And thank you to the Royal Institution and the Royal Academy of Engineering for hosting this event and inviting me to speak. And thank you all for coming along to be part of the discussion on the secret superpowers of the seabed. So I'd like to take the opportunity to talk a bit about how offshore wind could help us reach net zero and why what lies at the bottom of the ocean is critical to harness the winds that blow far above. But first, let us have a step back and look at some of the known pieces of the energy puzzle. So the warming stripes are a familiar image to many, I think, a visualization of long-term temperature trends where each bar shows the average temperatures within a particular year and clearly shows the acceleration of global warming as a result of increased greenhouse gas emissions in the atmosphere. And anthropogenic activities are driving that increase in greenhouse gas emissions, and energy production from burning fossil fuels is responsible for 75% of anthropogenic greenhouse gas emissions and 92% of anthropogenic carbon dioxide emissions. And of course, we all use energy every day, all of every day, and even while we're sleeping. So all of these things require energy at our point of consumption, but these, along with many other things that we use in our everyday lives, require energy for manufacturing and to ship the components or the manufactured goods to us as consumers. Now, the Royal Institution is a very apt place to be talking about energy because Michael Faraday, who was a young employee here and then director of the Royal Institution Labs, his discoveries of electricity generation and transmission have helped shape this modern world. So we have an energy-intensive lifestyle in the UK, of course, but there is a stark variation in energy consumption across the globe. And we can see that in the map here, where the darker red colours show higher energy use per person. And we can see from the map, for example, that the average American uses about the same amount of energy in a month as the average Indian uses in an entire year. And the average Brit uses about double that of the average Brazilian. And that the top 10 greenhouse gas emitters contribute about 2/3 of global emissions. So where does all this energy come from? So the current global energy balance derives from fossil fuels, which are oil, coal, oil and gas, from nuclear energy and from renewable resources, mostly hydropower, wind and solar. And what we can see from the graph here is that about 80% of our current energy balance derives from fossil fuels, and our consumption has been increasing with time, year on year, and at a rate outstripping population growth. Now, the proportion of energy that is produced from renewable energy or from fossil fuels also varies across the globe, as does energy consumption. And in this map here, the darker green colours show the countries with a higher proportion of primary energy generated from renewable resources. But what is interesting to note is that it is a non-linear scale. So when we're halfway along this scale, we're still at countries producing less than 10% of the final energy from renewable sources. So while some countries are doing better than others, it's pretty low everywhere. So what are the renewable energy sources that currently provide us with energy as a logical starting point to trying to think about how to decarbonise the rest of the energy economy? So renewable energy is harnessed from the power of water, the wind and the sun. And hydropower from water is the most common type of renewable energy, comprising about 50% of the total. Wind is next at about 25%, and then solar of 15%, and the remaining 10% from other renewables. So let's take a quick look at how electricity is generated from water as the most common type of renewable energy. So the principles of a modern hydroelectric plant are very similar to those of a traditional water wheel, where flowing water turns the paddles of a wheel which drives a shaft, which would then have driven millstones to grind the wheat into flour. And here we can see a modern water wheel as part of a hydroelectric plant, where flow from water in a reservoir turns the turbine, which drives the generator, which makes the electricity that can then be transmitted to consumers via the grid. And we have a bit of a demo here to demonstrate how that kinetic energy of the water is converted into electrical energy to make the light up. So Dan here is the head of the demo team here at the Royal Institution and has created this fabulous hydro-powered lighthouse for us. Take it away. And there we can see, and a free shower as well. Thank you, Dan. So while hydroelectricity is likely to continue to be part of the energy mix, there are some environmental and social concerns over hydropower, particularly flooding valleys, which changes ecosystems and can displace communities. And equally, increasing droughts and temperature rises and heat waves are reducing the amount of water flowing into the reservoirs that are powering the hydropower plants. And so it's prudent perhaps to look, as water becomes a more scarce renewable resource, to look at wind as an abundant renewable energy resource and the second most deployed renewable energy already. So wind power is also generated from a turbine similar to hydropower, but in this case the kinetic energy of the wind moving through the blades is converted into electrical energy, which can then be transmitted to us as consumers. So Dan is going to come back and he's going to instantaneously convert our hydro-powered lighthouse into a wind-powered lighthouse. Thank you. So another fun fact sort of related to the Royal Institution is that this casing, which holds the gearbox and the generator on top of the tower, and the wind turbine tower itself, act as a Faraday cage named after Michael Faraday. And it protects the interiors of the wind turbine from the electromagnetic radiation from lightning strikes, which is a common form of outage at wind farms. There's the lightning. So there's a long history of wind power too, initially to mill grain into flour, and to today's modern turbines that generate electricity. And modern day turbines can be built both onshore and offshore, meaning that the turbines are built on land or in the ocean, as we can see from the photographs. Now, since the Industrial Revolution, we have been burning fossil fuels to drive turbines, and it's really important that we go back to using renewable resources to generate electricity at the scale that we want to consume it. And wind is abundant, so it's good to pursue as a way to decarbonise the rest of our energy economy. So offshore wind has, or wind power in general, has been increasing over the last 2 decades by about 40-fold. And what we can see from this graph is actually the vast majority of wind is generated by onshore wind turbines, which is shown in the green columns, and the blue at the top of the columns shows offshore wind. But it has been increasing and getting more popular. And we can see that more clearly here, showing the growth of offshore wind since the installation of the first commercial offshore wind farm in 1991 to install capacity of more than 63 gigawatts at the end of last year. But this growth rate is quite eclipsed by the forecasts for 2,000 gigawatts of installed offshore wind by 2050. And this map helps to explain why offshore wind is gaining in popularity, because it shows wind speed measured both offshore, around the coasts, and onshore at fixed elevation above sea level. And the higher wind speeds are shown by the reds and the purples, and we can clearly see those clustered more around the coasts than on land. Now, mean power density, which describes the potential power output per unit swept area of the turbine, is a clearer and it's a more meaningful metric for describing power generation. And we can see, using that metric even more starkly, the benefits of offshore wind. And we can see a very purple patch, literally and figuratively, around the UK and Northern Europe. And indeed, the UK has been a leader in installed offshore wind for 2 decades, and much of the rest of the capacity has been generated across Northern Europe. China has emerged strongly in the offshore wind market over the last decade, and since 2021 has been the top installer of offshore wind. But considering the UK, what does it mean to us that the UK has led the world in offshore wind installation for the last 20 years? So here we can see the percentage of UK homes that annual electricity needs that can be met by offshore wind rising from 4% in 2011 to over 40% in 2022. And there are clear ambitions to increase this capacity, as set out in the government strategy documents that we can see here, reaching up to 50 gigawatts by 2030, just 6.5 years away, and requiring an installation rate of over twice that achieved to date. The UK's sixth carbon budget has set out targets of up to 140 gigawatts by 2050 to decarbonise UK electricity, and up to 226 gigawatts to decarbonise electricity and also meet the growth of the UK hydrogen economy. So hydrogen is the front runner for decarbonisation of liquid fuels, which is also essential to decarbonise our energy economy, because currently electricity only accounts for about 20% of our total energy consumption globally. A lot of energy consumption relies on liquid fossil fuels, particularly for transport for cars and trucks, ships and aeroplanes. So hydrogen is abundant in the environment, but to produce hydrogen as a fuel, it's got to be separated from the other elements in the molecules where it occurs. And there are many ways of producing hydrogen. The most common are steam methane reforming and gasification or electrolysis. And all of these methods require a lot of energy to carry out. And the vast majority of hydrogen currently produced relies on the burning of fossil fuels to produce the hydrogen. But electrolysis with renewable energy could make potentially green hydrogen, but will need immense renewable energy reserves. So, in another connection with the Royal Institution, Michael Faraday discovered the laws of electrolysis in 1833, and this involves using an electrical current to separate the water molecule into hydrogen and oxygen with electrodes, which is the current method of making hydrogen. So back to the UK energy scenarios, and our most ambitious includes growth of a domestic hydrogen market as well as an export market with up to 466 gigawatts by 2050. So I realise these just sound like maybe big numbers, but what we can do is compare this to today and realise that we need to be producing something of 30 times more the amount of electricity from offshore wind than we are currently. And with some rough scaling, this would mean something of 50,000 offshore wind farms by 2050, compared to about 3,000 currently installed around the UK at present. So, the need for tens of thousands of new offshore wind turbines begs the question where to put them all. And sometimes we think of the ocean as an empty space, but it's actually quite busy with shipping lanes, existing offshore wind infrastructure, existing offshore oil and gas infrastructure. There are no-go zones that are controlled by the Ministry of Defence, and marine protected areas for endangered species or for breeding grounds. And of course, the ocean provides the habitat for all of marine life. There are also metocean and geoscience conditions that make some areas more or less attractive to develop offshore wind farms in. And so we're looking at just this challenge in a piece of work by collecting these vast data sets of the metocean, the geological, the ecological and the anthropogenic conditions and constraints, and collating all of this into a database that we can interrogate through geospatial analysis. And this allows us to identify sea regions that are equally or less crowded than current offshore wind farm sites, so as to inform policymakers where the future offshore wind farms could go. And what we can see from this piece of work is that different sea areas around the UK, which are indicated by those different bars, have got different amounts of available space, which is defined by the height of the bar, and different amounts of crowdedness, which is defined by the type of fill. And ultimately, the nearly half of the available space is going to be required to meet our most ambitious energy targets. What we can also see from this study is the vast majority of available space is in water depths more than 60 metres. And this is significant, and we're going to come back to this later. And so there's a similar challenge for marine spatial planning across the world. And we can see here to meet the 2,000 gigawatts target could require something of 200,000 offshore wind turbines, which need to be installed at a much faster rate than has been achieved to date. So we can talk about 200,000 offshore wind turbines, but what does an offshore wind farm look like, and how many houses could it supply with electricity? So here is a lovely photograph of an offshore wind farm. It's the Horns Rev 1 in the Danish North Sea. It's actually quite an old wind farm, about 20 years old, but the template is largely unchanged, and it's a very beautiful picture. So the current largest offshore wind farm in the world is the Hornsea 2. It's 90 kilometres off the Yorkshire coast in the North Sea, and it comprises 165 turbines, which is about twice as many as we can see in this picture for Horns Rev. They're bigger turbines as well, 8 megawatts at Hornsea 2, and generates 1.3 gigawatts of green energy to supply 1.4 million homes. And Hornsea 2 covers an area of 462 kilometres squared, which is about 1.5 times the size of inner London, or 20% bigger than the Isle of Wight if you come from my area. So Hornsea 2 comprises 8 megawatt wind turbines, which we can see from this image has got a rotor diameter of 167 metres, such that each blade has got a length equivalent to the wingspan of an A380. And we can clearly see this evolution in the size of offshore wind turbines from the installation of this first one in 1991 through to predictions of 250 metre diameter turbines by 2030. So why this drive for bigger and bigger turbines? So this is because the amount of power that can be harnessed from the wind is dominated by the size of the turbine. Through firstly the swept area of the turbine, so longer blades, you can sweep more area and harness more power or wind. And secondly, because wind speed increases with elevation. So the bigger and the higher up the turbine, the faster the winds that can be captured. Now we can see from the power output equation that the power output is related to the square of the rotor diameter through that area term and to the cube of the wind speed. So if you doubled the rotor diameter, you could quadruple the power output, and if you double the wind speed, you could theoretically increase the power output by a factor of 8. And this really helps to understand why offshore wind is so much more attractive when we look back to that map with the reds and the purples all around the coast showing the much higher wind speeds. And so we can see here on the right-hand side, these are power output curves for different rated turbines. So as they get bigger, swept areas and higher wind speeds, the power output increases. And if we compare onshore and offshore wind turbines, we can see that offshore, the turbines are much bigger. These are average sizes from 2021. And so we can see that a 40% increase in the diameter of the blade from onshore to offshore leads to something of a threefold increase in power. And we can see that from the statistics from the UK, where we have a similar amount of wind capacity both onshore and offshore, but actually about 4 times as many onshore wind turbines as offshore wind turbines. So back to the ocean, and when we look out to sea, we see these majestic blades rotating across the horizon. But what is going on below the waterline to keep them stable and keep them in place? So there are actually a range of architectures for offshore wind turbines, both a fixed concept, which means there's a continuous structure between the seabed and the turbine, and floating architectures for deeper water, where a floating platform is secured to the seabed through mooring lines and anchors. So the variety of ways of securing them to the seabed are illustrated here. So starting from the left, we've got a gravity-based foundation. So this is just a heavy weight, really, similar to the the concrete block or the water-filled block on the bottom of the garden parasol or the swing ball. We've got skirted foundations, which are really like an upturned can or bucket. The monopile, which is an open-end tubular steel pile. And this is the most common type of offshore wind foundation. About 80% of all the existing offshore wind is supported on monopile foundations. And then there are deep piles, which are very similar. They're just slenderer, so they're smaller diameter and longer, and can be used for both fixed concepts and for floating concepts. So as foundations for the fixed and anchors for the floating concepts. Other types of anchoring systems involve suction caissons, which are really like long skirted foundations. And they differ from monopiles because they have a seal top with a valve on, which means they can have a neat method of installation and also a neat way of mobilizing capacity. And we're going to have a look at that in a minute. And another sort of anchoring system is a plate anchor, which, as suggested by the name, are just plates of various shapes that resist the mooring line forces once embedded into the seabed. So we're going to have a demo now to have a look at how we install some of these foundations and how they mobilise their holding capacity. So for that, we've got Dr. Catherine Kwa, who is a Royal Academy of Engineering research fellow who works in the group at Southampton. And shall we take away the lighthouse? Here we go. So for the demonstration, we've got 3 different types of anchors. So we've got a traditional pile, deep pile foundation. We've got a plate anchor, which is, we've got a screw pile or a helical anchor for our plate anchor, and then a suction caisson as well, which we can see is attached to a giant syringe rather than a suction pump. So starting off by installing the traditional pile. So in reality, these piles are driven in place, so a collar is put on them and they are hammered in place, as is being demonstrated by Catherine here, hammering the pile into the seabed. Okay, so next we've got the plate anchor, and there are a variety of different types of plate anchors. We've got another sort here, which is by far the most conventional type, and this is installed by laying it on the seabed, and you pull the mooring line and the anchor self-embeds itself. But you need a lot of travel for that we haven't got room for. So we're going to use a screw anchor as our type of plate anchor, which we apply torque to. So here's Catherine applying this torque to install the plate anchor into the seabed. And you can see that's quite hard work. And then we've got the suction caisson. So these were the ones I was talking about with the sealed top cap and the vent. And in reality, a suction pump would be attached to the vent, and the self-weight of the foundation, which in reality would be very heavy, or the anchor, when it's put down on the seafloor, would allow it to self-embed a little bit. So we're giving it a little bit of help to start off with. And then the suction pump is turned on. Oh, the magic is not working. We've got water in our system, but we're going to have another go at that. There we go. Right. So we're going to flood is it flooded? Excellent. Okay. Okay. Here we go. And see the magic. It's a bit murky, but honestly, it's installed itself. Thank you. And so, although, it made a little bit of spluttering noises, it's actually a much quieter type of installation than the hammering, so it's a much more environmentally sensitive way to install foundations offshore, because the hammering noises really disturb marine life. So now we've got them all in, let's have a look at the resistance that they can mobilise. And so really, in reality, you'd have your floating turbine above the anchors, and then the environmental loads would push on the wind turbine and it would move across and apply some load to the anchor, and they have to be designed to resist those loads. We're going to pull them all out just vertically so we know we've got a good straight comparison, and all with the same spring balance. So let's start with the pile foundation. If we watch the plunger go down, you can see that really didn't mobilise much resistance at all. It does mobilise more than the weight of the anchor because it's embedded in the seabed, and so the frictional resistance just around that external shaft gives it a bit of extra capacity, but not much. So let's have a look at the plate anchor next. So here, pulling up on the plate anchor. Got that there. So, okay, we're going to start pulling up. Watch the plunger go down. And we can see we're mobilizing plenty of capacity there. And up comes the plate anchor. We can see that it's brought up... We can see that it has brought up some sand with it, but it's not just the weight of the sand that improves the capacity. In order for this plate to move up, it has to mobilize a large bulb of soil all the way around the plate, which is what gives it this bigger holding capacity. Okay, let's go with the suction case on now, Catherine. So remember, this had a really nice, environmentally friendly way of installing it, and let's see how it performs. Yeah, so again, very nice capacity. I'm a bit worried about the people in the front row. And look, there we go, fantastic. So really good capacity from the suction case on it. It's quiet to install, and it provides really good capacity. So we can have a round of applause for the suction case on, and Catherine. Thank you. We got that? Okay, fantastic. Okay, so we had our model foundations here, but of course in reality these foundations and anchors are huge. And here we can see some examples of real ones. In the top left we've got gravity base anchors, then followed by skirted foundations on a jacket structure, a deep pile foundation, suction caisson in the bottom left, more suction caissons in the middle there with the mooring line chain shown in the foreground. And on the right-hand side, we've got one of these drag embedment anchors ready, a different sort of plate anchor ready to be deployed. And in each of these photographs, there is a boat or a truck or some people that can give you a sense of the scale of these structures. And the chain is shown there to show that it's really not just about the anchor either. There's a great deal of raw materials required for the mooring chains as well. So not only are they very big, we're going to need lots and lots of them, up to 100,000 foundations just in the UK. And as we saw earlier, about 90% of the available sea space in the UK for future offshore wind is in water depths more than 60 metres deep. And this means that it's going to require floating technology. So not the fixed architectures that are much more common, but the newer floating technologies. And this requires considerable innovation to be able to install that floating offshore wind at the pace and scale required to meet net zero. And without innovating in new approaches in offshore design, supply chains for steel and other materials are going to be stressed. Just as an example here for a rough calculation, for anchors and mooring lines around the UK by 2050 could require somewhere upwards of 30 million tonnes of steel. So every year between now and 2050, this would be about 20% of the UK annual steel production, which of course there is great competition for from other sectors, including the rest of the wind sector. About 90% of the mass of offshore wind turbines is made from steel, and other large sectors like construction and automotive rely heavily on the steel sector. So we need to innovate to meet the demand. We need to be able to meet this pace and scale of our offshore wind ambitions. So we need to urgently rethink our traditional design approaches to be able to improve our anchor system performances, because then they become more efficient, so we can have smaller anchors and mooring lines for resisting the same loads. This will reduce pressure on the supply chains. There'll be less embodied carbon in the infrastructure. They'll be easier to manufacture and to install. They'll be more economical, and importantly, and as we'll see later, they'll also be more reliable. And so there are various ways we can go about trying to improve anchor system performance, and we're going to have a look at a few now. So let's start off by looking at how to use less anchors as a way to use less raw materials. So one way to use less anchors is to use bigger turbines, because as we saw earlier, the power output is going to increase at a faster rate with increasing turbine size than the size of the anchors. So we saw before that the power output is related to the square of the rotor diameter and the cube of the wind speed. whereas the size of the anchors is more likely to linearly increase with the size of the floating platform. So another approach to using less anchors is to try and share a common anchor between two adjacent floating offshore wind farms, as illustrated here. And in the honeycomb picture at the bottom, we can see a single anchor attached to three adjacent platforms shown by the yellow squares. Now, the loading applied to these shared anchors is much more harsh and complex than if it was just associated with one wind turbine. So we all know the best way to get a tent peg out is to really, waggle it about and twist it while we pull it out as well. And this kind of waggling is exactly what is happening to shared anchors. And so in order to be able to develop design guidance so they can be taken up in practice routinely, we need to understand better the response to this very complex loading. And we are exploring the response of shared anchors using a geotechnical centrifuge, which you can see here on the left. So it's essentially a rotating arm and a swinging platform. And on the swinging platform, there is a box. And inside the box, we can put soil, which represents the seabed, and then a model anchor, and some equipment that means that we could apply loads or displacements to the anchor that would represent the loads that it would really experience in the field, as well as some sensors to measure the response of the soil and the structure to those imposed loads and displacements. So in operation, the arm rotates. We shut the doors first, and Nor, who's in that picture, she leaves the room first. You shut the door and you turn the centrifuge on, and it spins around. And as it spins around, the platform swings up, very similar to when you try and swing a bucket of water around. And then the model is subjected to very high accelerations, and this increases the stress level in the soil, which is really important for geotechnical engineering because the response to soil is stress dependent. And so it raises the stress levels in the soil to the levels that you would expect to see in the field for those much larger conditions, those much larger sizes. Now, this scaling up of stresses means that we can scale down the length dimensions. So this means that if the centrifuge was spinning at 100 G, we could reduce all of the dimensions by 100. So a 50-metre long suction caisson could be modelled with a 15-centimetre anchor. The centrifuge is also somewhat of a time machine because of these scaling rules, and this means that we can model the full lifetime of loading, so over 25 years to an offshore wind turbine in less than 24 hours in the centrifuge. So this means we can look at field-scale stress conditions over a full design life by using small models and in a realistic time frame. And in this very controlled environment where we can really scrutinise the response of the foundation and the soil. And this enhanced understanding allows us then to be able to create design methods that can turn into design guidance to be taken up in practice. So a second way to improve anchor performance is to use anchors with the best efficiency. So efficiency is a measure of the capacity that an anchor can provide divided by its mass. So we saw some examples here in the demo, but if we take the simplest example of a heavyweight gravity anchor on the seabed, this has very low efficiency, actually less than 1, because the buoyant weight of the mass is less in water than it is on land. Once we have some embedment into the seabed, then the efficiencies increase. So for the pile-type foundations, capacities are usually 10 to 100 times the mass of the foundation. And we saw more for the suction caisson than for the traditional pile, because the traditional pile is gaining a little bit of extra resistance by just being embedded in the seabed, but just the frictional resistance around the shaft, where the suction caissons are mobilising a much larger mass of soil. But plate anchors are generally the most efficient type of anchor and can have efficiencies up to 1,000 depending on the soil and loading conditions. And this is really because generally the amount of steel left in the seabed is smaller compared to the pile foundations, but they have similar capacities. And so this unlocking of the additional capacity of anchors by just having them in the seabed is something of a seabed superpower. And based on this graph, you should think we should just use plate anchors for everything. But actually, pile foundations are much more common for mooring permanent structures because there's much greater certainty about the final embedment depth and the methods of installation too. We saw with this drag embedment anchor, there is some uncertainty about exactly where it will end up in the seabed, and this affects the capacity that can be mobilised. And we saw the helical pile or the screw anchor in the demo as well. And these are actually very popular onshore, but for the scale needed offshore, the torque, the turning to install them is actually a challenge that has yet to be overcome. So this piece of work uses a computational method called discrete element modelling, which allows us to scrutinise the microstructural response of the seabed as the helix cuts through it. And by better understanding this micromechanical response, we can optimise the shape of the helix. And this piece of work ultimately showed that by optimising the helix at a particular angle to the shaft, you can use much less torque to get the plate anchor in than you would otherwise predict. And so, of course, that brings screw anchors at a scale needed for floating offshore wind much closer to being a reality. So, a third way to optimise mooring systems in order for us to be able to meet net zero by being able to reduce the amount of required steel, for example, is to try and reduce the loads that are applied to the mooring system and the anchor. But of course, we cannot reduce the wind or the wave loads, but we can reduce the amount that is transmitted to the mooring line and the anchor by including a so-called load reduction device, which is essentially an extensible portion or a stretchy section of the mooring line. And there are a couple of examples shown here. The first one is a spring-type structure, and the second one on the bottom is more of a pendulum. But they work on the same principle. They have this nonlinear stiffness response, and they provide additional extension to the mooring line when the platform is displaced by the environmental loads. And this ultimately causes a reduction in the amount of load that is transmitted through the mooring line and into the anchor, as we can see from the coloured curves in these two plots, and they are plotted against the grey line, which shows the loads transmitted to the mooring line and anchor in the absence of the load reduction device. If you want to use a load reduction device, the design question that you really need to answer is, what is the length and the rated load of the load reduction device that you need in order to minimise the loads transmitted to the anchor and the mooring line within acceptable platform displacements or movements for some given environmental conditions. But this is not actually the question that is answered with traditional design of mooring systems, which usually will model the entire floating system, so the floating structure and the mooring line, and it will take in the characteristics of your mooring line, it will take in the environmental loads, and the output will be the platform displacements and the tension, which are not the things that we really are interested in. So you do the analyses, and then if you find that it's not actually acceptable, then you change those input parameters, your mooring line characteristics, and rerun the analysis until you get to a workable solution. Now, you can get to a workable solution, but you don't know it's an optimal solution, you just know that it's safe. So a piece of work that we're carrying out at the moment is to try and address this design question directly, to be able to find an optimal solution and do it in a reasonable time frame. And so we've done this by creating a surrogate model, which has been trained on tens of thousands of traditional analyses. And then with the surrogate model, which is created with AI, so it's an artificial neural network, it runs much more quickly than these traditional analyses, we can use an optimization routine to be able to iterate through to an actual optimal solution. And for a case study that we looked at on the west coast of France, we were able to show more than a 50% tension reduction and more than a 70% reduction in foundation footprint compared to a conventional chain catenary mooring. So of course this just translates into really much less steel required for the anchors and for the mooring line. So the fourth opportunity for innovation to help us meet the pace and scale of offshore wind requirements is by relying on even more seabed resistance. So we've had a look at how the seabed can enhance the capacity of anchors just by being embedded in the seabed. But we can ask the seabed for a bit more. And in order to talk about this a bit more, we need to understand what happens when we load soil. So for this case, we're going to take a simple gravity anchor resting on the seabed and a highly idealized seabed sediment of these rectangular packed spheres. So this is quite a loose configuration. So initially, the weight of this foundation that's just been added will be carried by the water in the pores, not the actual grains themselves. And at this point, the soil is at its weakest, because soil is a frictional material and it gets its strength from the interparticle friction. And these water pressures that are increased because of the load that has been put on them kind of pushes them apart, and their interparticle friction reduces. So it's weaker, but with some time, all the water will seep out, the particles will rearrange into this denser configuration to accommodate the load, and the soil will become stronger. So you see here we have 2 bars of strength instead of our initial 1 bar of strength. Now in sandy or gravelly materials that have got quite a big particle size, these changes in density can happen quite quickly. In softer and muddier soils, it can take a bit of time because the particle sizes are much smaller, and these drainage path lengths for the foundations could be 30 metres or more. But nonetheless, we can show that you can get this improvement in the strength of the seabed in a sufficient time to be able to optimise the size of your foundation from the get-go before, say, the winter storms come, or just before you install the mast and the turbine, which is what attracts those large environmental loads. And so really, this is unlocking additional capacity from this evolving seabed resistance. So just by using the seabed, we can make it stronger, which is really a seabed superpower. In this graph here, we can show how you can reduce the required size of a foundation by understanding this evolving seabed strength. And so in this example, you could use a foundation that was half the size that you might otherwise predict with traditional methods. Now, reliance on strengthening of seabeds can be applied with even greater benefits when you have through-life cyclic loading of offshore infrastructure. So if we consider a plate anchor securing this floating offshore wind structure here, initially we can see the plate anchor in our seabed, and with cyclic loading, from those environmental loads over time, the soil, particularly above the anchor, will densify and become stronger. So again, the 2 bars of strength. And then this will continue to happen continually throughout the design life of the structure, not just the one-hit wonder from the self-weight of the platform, but throughout the life it will keep getting stronger and stronger. So again, that evolving strength through the life of the structure is really a seabed superpower. And it translates into reduction in the size of anchors that we need. In this particular study, we could show that you could reduce the size of your anchor by nearly 40% by relying on seabed hardening. And if you couple the seabed hardening with a load reduction device, this extensible section in the mooring line, you can reduce the size of the anchor required by over 50%. So ultimately, this means doubling the efficiency of the anchors, so you can get twice as many anchors for the same amount of steel. But actually, capacity is only half of the story, but it's not only halfway through the presentation. So designing infrastructure isn't just about making sure it doesn't break or catastrophically fail, like, for example, this suction case on being dragged clean of the seabed. This type of calculation is governed by the strength of the seabed and is so-called capacity. But it's also necessary to ensure that infrastructure doesn't move or displace too much, just so it can continue to perform the function that it was designed for. And stiffness rather than strength governs displacement. But stiffness also evolves throughout the life of the infrastructure, as does strength, and in proportion with each other, as they're both dependent on the density of the soil. So as the soil gets stronger year on year, the soil will also get stiffer year on year. So if there was a prescribed limiting displacement for a particular type of structure, then the maximum load that a structure could withstand year on year would increase. Or if there was a particular operational load, like the peak load in a winter storm, for example, then the amount of displacement that would be incurred would reduce year on year. And this could be really useful for accurately predicting, say, the ratcheting of these shared anchors that are under this very harsh and complex loading. So each year, the incremental displacements would reduce by taking account of the increase in stiffness. And this is contrary to traditional design methods, which would consider only continual weakening. So those incremental displacements would just get bigger and bigger every year, which ultimately means you need to start off with a much bigger anchor. So increasing stiffness can be very useful for optimizing the size of an anchor for a floating structure, but it can be troublesome for a fixed structure, particularly for monopile foundations, which are governed by their whole system stiffness. Now, monopile wind turbines are designed so that the natural frequency of the system falls between the frequency of the rotor spinning and the frequency of the blade passing. And this becomes a bit of a moving target as the stiffness is evolving. And indeed, not taking account of this evolving stiffness in the past has led to troubles with operation and fatigue of the structural elements of monopile wind turbines, not surviving their full design life. So it's really important that we understand this evolution of the seabed property so we can appropriately design the infrastructure at the start. So this continuous evolution of seabed properties throughout the life of a structure is captured by an emerging philosophy called whole-life geotechnical design. And it differs from traditional geotechnical design by capturing both the hardening as well as the softening of the soil. So the softening is that initial part where the load is carried by the water and the soil is at its weakest. Whole-life geotechnical design also captures the hardening in between those periods of softening and throughout the life of the structure. So if we consider starting from the beginning here, so there will be some loading and the soil will reduce its strength. It's a bit like going for a long run and you feel fatigued at the end of it. So with some time, the soil will regain its strength as we would, and in fact our fitness would be improved and we would be better for the next run. Doesn't mean we won't be tired after the next run, but we'll be in a better state than we were after the first one. And it's the same for the soil, and this goes on through the life of the structure. And so we've seen that the strength will evolve through the lifetime of the infrastructure, but so will the stiffness, and indeed will the permeability, which is the rate at which that water can flow between and out of the pores. And so the permeability will also increase, and that will mean that the rate at which the changes in strength and stiffness also change year on year. And so this continual enhancement of seabed properties allows for more efficient and reliable foundations and anchors, really taps in to the seabed superpowers. So we've talked about how seabed properties can evolve over the lifetime of the infrastructure from that day-to-day loading. We can also rely on a second seabed superpower to resist very short loads that might be a snatch load during an extreme weather event. And it's been shown that this dynamic capacity, which is a function of the acceleration of the mass of the shear failure mechanism, which we can see by those red bulbs around the plate anchor there, which is what was happening in the sand, but you couldn't see it. This shear failure mechanism, if we consider the acceleration of that mass, we can get this extra dynamic capacity as well, which has been shown to be up to 50% more than the static capacity for plate anchors in soft soil. And this ultimately allows us to use smaller anchors from the start. So we can see there is a recurring theme. So looping back, we've seen various examples of innovation underway to improve our anchor and foundation system performance, and that will enable us to meet our collective offshore wind ambitions to achieve net zero. So there is another essential focus for innovation in order to meet our offshore wind ambitions, and that is acquiring the actual seabed parameters that we need for these design methods. And this is an example of some site-specific offshore geotechnical data from the Burbo Bank, which is in Liverpool Bay, off the coast of the UK. And here we can see it's a 7-kilometre wide site, and each of those dots along that transect are represented by one of those graphs at the bottom, which show profiles of seabed resistance with depth. And these are measured by a tool called the cone penetrometer test, which is basically a cone on the end of a rigid shaft, which is penetrated into the seabed, and the resistance is measured. And what we can see from the graphs is that seabed resistance can vary quite dramatically with depth and with distance across the site and over relatively small distances. And this poses a real challenge for offshore wind, as the area of seabed that needs to be characterised at design quality and resolution is really vast, of the order of 100,000 kilometres squared just for the UK. And this level of seabed characterisation is really a shifting challenge as we face the energy transition. As site characterisation for a single hydrocarbon platform, which is what there is experience of in the past, require far fewer sites of much smaller area and a greater focus on capacity, so just strength measurements. And this is still not a trivial task to do this offshore, but the challenge is increased greatly for offshore wind, where there are many more sites of much greater size and a greater emphasis on displacements as well. So we need strength, stiffness, and permeability. And so this really presents an urgent need for us to be able to characterise large areas efficiently and effectively, and that is not the case for current site investigation methods. So this image here shows how current site investigation is carried out, and it requires big vessels with lots of equipment and people on board. And there's usually two parts of the investigation, a geophysical investigation and a geotechnical investigation. So in the front here, we can see the vessel is the geophysical boat, and generally, it sends acoustic pulses to the seabed, which are then reflected back and collected by those streamers that are being towed behind the boat. And the geophysical investigation gives a bit of an indication of the types of material in the seabed and the location of interfaces between different types of seabed, but it doesn't tell you what the geotechnical parameters are, the strength, the stiffness, or the permeability that you need for the engineering design. The geotechnical investigation gives you that. And so that's the vessel in the background there, which we can again see is a large crewed vessel, maybe 40 people on board, a big drilling derrick, and it will have a drill or a seabed frame lower to the seabed to carry out intrusive tests like the cone penetrometer test, and also to take boreholes from which samples will be then sent back to the laboratory for testing, usually for stiffness and permeability. So in the geophysical investigation, the boat goes up and down, and back and forth in order to acquire the data to create essentially a 3D map of the seabed conditions, but not the engineering parameters, but other geophysical parameters. The geotechnical investigation, by contrast, collects those parameters that we need for design, but only at those discrete locations shown by the circular markers. And we can see from the middle picture that we have a continuous profile of resistance with depth from that cone penetrometer, but only discrete samples for stiffness and permeability from the boreholes. Now, additional complexity is that due to the compressed timelines of offshore wind development, you often don't know the exact location of the wind turbines when you go out to do the site investigation. And so the geotechnical engineer might find themselves having to interpolate between adjacent boreholes or CPT profiles in order to do the design. And as we saw from the Burbo Bank site, these seabed properties can change quite a lot over quite small distances. So in terms of an innovation that will help us to overcome this challenge, there is an emerging body of work to try and extract synthetic geotechnical parameters from the measured geophysical parameters. So because that is continuous, so if we could extract the geotechnical parameters from it, it would be great. So there is this body of work that correlates the measured one-dimensional profiles of geophysical data, usually acoustic impedance, with the measured seabed resistance from the CPT. And by using machine learning, it's basically a blind correlation to match them up. And this means, given some geophysical data, you can predict a synthetic CPT profile, which has obviously got immense potential. But it does only give us strength, and what we really need is the stiffness and the permeability as well. But remember, we've only got a small amount of data for stiffness and permeability from these samples that are taken to the laboratory. So the same machine learning techniques can't be used to get the stiffness and permeability that are being used to extract the strength profiles. So a current piece of research that is aiming to overcome that scarcity of the geotechnical stiffness and permeability data is using synthetic, or trying to create the synthetic data by using micromechanical computational models where we have known geotechnical input. We apply an impulse and monitor the geophysical response of that wave moving through it. And with that, we can train an artificial neural network. And then from the artificial neural network, we can take field geophysics and hopefully extract these synthetic profiles of stiffness and permeability. So I promise I'm really cantering on to the end here. So one other thing that we really also need to innovate in is the actual hardware and the tools to collect some of this geotechnical investigation, to either collect data that is more useful for the design that we want to do these days, or that doesn't need such big vessels to deploy the equipment. So this here is the RoboCone project, which is an extension of the traditional cone penetrometer test, which is a rigid shaft. But the RoboCone has got these robotic elements that either jut out or twist around or move up and down. And this allows us to acquire much more useful parameters, and particularly those that will help us to do whole-life geotechnical design. And here we've got a couple of images of some hardware that has been developed by groups of students at the University of Southampton as part of their group design projects. So the first one here, NESI, the Near Surface Site Investigation Equipment, couples the use of a traditional CPT, cone penetrometer test, with the suction caisson, which we saw in the demo here. So we've got the suction pump attached to it here, and that drives in the suction caisson, just like we saw Catherine do here. And those pantograph arms give you a mechanical advantage such that you can drive in a CPT that's 3 times longer than the skirt of the foundation into the seabed. And then you can pump water back into the caisson and it comes out again. So the NESI can be lifted up, moved to the next spot and redeployed. And it's been designed to be able to be deployed from an autonomous vessel. So no need for the large crewed vessel for these tests. This is the GeoIBot, which has also deployable from a small vessel because it's installed by freefall through the water column, penetrates into the seabed, and then it actuates itself based on a worm. So it's got this fan that comes out to provide the resistance so it can move itself along. It's got some actuation so it can change direction in the seabed. And at the end, it's got a traditional cone penetrometer test so we can collect the resistance data. A pore pressure sensor for permeability measurements, and this expanding bladder for stiffness measurement. So these might be slightly fanciful, and they're certainly very low TRL level, but they give an indication of the type of vision that we need in order to be able to transform the way we do offshore site investigation, in order to be able to deliver the offshore wind ambitions. So future vision for offshore site investigation could be a swarm of these autonomous vessels carrying out geophysical and geotechnical site investigation. And this approach could also be used for post-construction surveys, not just of the structures, but of the seabed, to really better understand how the seabed is evolving as we're predicting it to. So looking to the future a bit more broadly, I certainly hope that we see abundant, accessible, affordable, and secure clean energy for all, and quite a proportion likely to be supplied by offshore wind. That there'll be innovation enabled by emerging technologies, so offshore wind can be installed at the pace and scale that we need in order to meet net zero. And that it's a just intervention in the ocean through collaboration with the environment, heritage, and society. And there are many technology-enabled solutions that will help affect those collaborations. And also to ensure that we consider the end of engineered life at the design phase in order to reduce the burden of the raw materials involved in delivering offshore wind and net zero. So looping back to the title of the talk, are seabeds the hidden piece of the offshore wind puzzle for net zero? Well, offshore wind is certainly an abundant renewable energy resource. All offshore wind has to be secured to the seabed, whether it's fixed or floating infrastructure. And as we've seen, the pace and scale of offshore wind is putting huge pressure on supply chains, and so we need to innovate in order to be able to get more out of less in order to deliver net zero. And we've seen that better understanding of that microstructural response of the soil and how it evolves rather than stays constant over its life really helps us to better design infrastructure of these supersized structures that we need. So really the short answer is yes. Unearthing the secrets and unlocking the superpowers of the seabeds that lie at the bottom of the ocean is critical to harness the abundant renewable resource that blows far above in order to achieve a net zero future. So I'd like to draw to a close just by acknowledging and thanking all my fabulous colleagues at the Centre of Excellence for Intelligent and Resilient Ocean Engineering, some of whom are here this evening, and my other colleagues across the University of Southampton and beyond. All of our external supporters and collaborators, and certainly to the Royal Academy of Engineering for supporting me and my research through my chair in emerging technologies. I'd like to thank the teams at the Royal Academy of Engineering and the Royal Institution for hosting this event and inviting me to give this talk. It's been an absolute pleasure and an honour. And thank you all for your time and interest in coming along to be part of it. Thank you.